Hi everyone, this is our second video example regarding our lecture where we talked about multiple unit processes. So in this problem, we are looking at question 4.7. We're just doing parts C, D, and E, and I'll talk a bit about parts A and B, describing an absorption column and a stripping column. This is on page 191 of your textbook. What I want you to do right now is actually turn to that page and read that question and try to understand it the best you can, and then restart this video and I'll try to explain a bit about what this absorption and stripping tower is. So this absorption unit is a typical chemical process. Again, it's a separations process where now we have a gas that it comes in contact with a liquid, and some portion of that gas or some component in the gas is going to be preferentially absorbed into the liquid. It's one of separations technique where you're trying to get rid of a particular component in a gas. So for example, let's say you have a process that generates a lot of greenhouse gases, and due to EPA regulations, you cannot just release it into the atmosphere. So what you want to do is to go through a process where you remove a lot of, for example, some of those greenhouse gases. Maybe you have SO2 in there. So what you're going to do is you're going to pass your gas through a solvent that will preferentially absorb out the SO2, and now you have a gas that has less SO2 in it that you can now release into the atmosphere. So part of how an absorption column works is that in general you're going to pass the gas through from the bottom of the column and the liquid solvent from the top of the column. This is just to reduce the amount of energy you need. Imagine trying to pump a liquid using a pump up a column to get to where you need to the top of the column. Instead, if you get it up to the top of the column and just let gravity do its work to go through the column, and on the other hand, you just pump your liquid from the bottom up to the top, and now you can contact the liquid and the vapor together. So what you're going to see in this problem is when they say the liquid goes in from the top, the gas goes in from the bottom, that's what it's trying to talk about. In general, you have an absorption column. It is in conjunction with a stripping column. Think about a stripping column as the opposite of an absorption column. So after you have passed your solvent through the absorption column, it has picked up a bunch of those gases that you don't want. You will want to recycle your solvent somehow. You don't want to just dump it and just waste it. So you'll pass it through a stripping column where now you'll pass another gas through this solvent that is rich in the gas component that you have pulled out, and the component that is dissolved in the gas will now come out into the vapor phase again, and now you have purified your solvent, and now you can put that back into your absorption column. So with that in mind, go ahead and read this question again, and hopefully it will help you understand it a little more. What is going on down here is that you have carbon dioxide and methane, and methane is sort of your product that you want to purify, so you want to get rid of the carbon dioxide. What you're going to do is you're going to use an absorption column. The solvent you're going to use is methanol. The methanol is going to preferentially dissolve the carbon dioxide and remove the carbon dioxide from the vapor stream. So you have a purified stream that is mostly methane, and that's your product. After that, that solvent is recycled or not, is passed into a stripping column where now you use a nitrogen stream to get out the carbon dioxide that you have absorbed from the vapor stream. And now you have purified your solvent again, you can recycle that back into the absorption column. All right, with that in mind, let's go ahead and go through this question and draw out the diagram. We have a process, we have an absorption tower and a stripping tower. To separate the components of a gas, we are told that it has 30% carbon dioxide and the balance is methane. This stream of gas is fed to the bottom of the absorber. A liquid that contains some dissolved CO2. The reason why it's not a pure solvent is because this is a recycled stream. We don't get everything out. So it has a tiny bit of dissolved CO2, 0.5 mole%. The balance is methanol, which is our solvent. It's recycled from the bottom of the stripper to the top of the absorber. Again, liquid comes out from the bottom, but we try to feed it to the top and let gravity do its work to pull it down to the bottom. The product gas leaves the top of the absorber, and it contains 1 mole% CO2 and all of the methane fed. So now you have purified the methane into your product, where it's just 99% methane. The CO2-rich liquid solvent, this methanol, has picked up a bunch of the CO2, leaving the bottom of the absorber, is fed to the top of the stripper, and a stream of nitrogen gas is used to strip out the CO2. And so 90% of the CO2 in the liquid feed to the stripper comes out of solution into the nitrogen stream. And this nitrogen CO2 stream passes out to the atmosphere. And the liquid stream leaving the stripping tower is that recycled solvent that goes back into the absorption column. All right, so now let's go ahead and draw this diagram. This is the part where in this question, what is challenging is really drawing the diagram and making sure that you don't have your process streams that crisscross all over the place, and it gets really confusing from there. So in general, even though the question describes it in a way that is practical and what is going on in real life, for example, the liquid going from the top, come out at the bottom, the gas comes in from the bottom, goes up from the top. For the purpose of drawing the diagram, don't worry too much about drawing a stream coming from the bottom and going back up to the top. In general, you want your streams to be straight, a direct arrow from one system to another. So we have an absorber and a stripper. Let's go over the question again. We have a feed stream containing 30 mole% carbon dioxide and the balanced methane, so that's our feed coming in. A stream of this gas is fed to the bottom of the absorber. I don't care that it's coming at the bottom. I like to put my feed on the left-hand side, so that's coming into the absorber. We have a liquid containing 0.5 moles% dissolved CO2 and the balanced methanol is recycled from the bottom of the stripper, so it comes from the stripper going into the absorber. And ignore the top and the bottom. All I have is a recycle stream that goes from the stripper into the absorber. We have a product gas stream that leaves the top of the absorber. That is our product stream. And ignoring the word top of the absorber, I have a product stream that comes out. And the CO2-rich liquid solvent, so we have this recycled solvent, picks up the CO2. This CO2-rich liquid solvent, leaving the bottom of the absorber, is fed to the top of the stripper. So it comes out from the absorber, goes to the stripper. Let's just draw a straight line through that. And this is mixed with a stream of nitrogen gas that is fed in through the bottom. So we have a nitrogen stream in the stripper. Once we have that, we have 90% of the CO2 comes out of solution, and you have a gas stream that has nitrogen and CO2 leaving that. And we have that purified methanol stream that goes back into the recycle. So that is our process flow diagram right here. Let's go back through the question again and label what we have in terms of information that's given to us. We have 30 mole% carbon dioxide and the balanced methane in our feed, so we are given the mole fraction. I'm going to skip ahead right now and say that if you read through the whole question, you realize that there's no basis given in this question. So I'm going to pick a basis in the feed of 100 moles per hour. You can pick a basis elsewhere if you want and make sure that you have the correct answer eventually. So we know that the mole fraction is 30% carbon dioxide, 70% methane. The next piece of information tells us something about the recycled liquid. It has 0.5 mole% CO2, and the remaining, that will be 99.5% as methanol. So we have the mole fraction in the recycle stream. The product gas leaving the absorber contains 1 mole% CO2, 99% methane. So we have the compositions of our product stream. Then we are told that the CO2-rich liquid solvent from the absorber goes to the stripper. No information is given there. 90% of the CO2 in the liquid feed comes out of solution. That's a process specification that we can't use for now. And the nitrogen CO2 stream leaving the column passes through another stack. So that's all we have. Everything else we have already labeled. Let's go ahead and fully label this diagram. In terms of the recycle stream and the product stream, all we are missing is the actual flow rate of those streams. In addition, in stream 2, which is our nitrogen stream, that is a pure nitrogen stream, so we don't need mole fractions. So those 3 streams, we just need the molar flow rates. So we put those in. In terms of stream 1 and stream 3, let's look at stream 1. In stream 1, we are told that it has the methanol that has picked up a whole bunch of carbon dioxide. We are also told that all the methane that comes into the feed goes into the product, which means none of the methane is going to go into stream 1. So in stream 1, we are going to have methanol and carbon dioxide. In terms of what's coming out of the stripper in stream 3, that is the stream where the nitrogen has picked up the carbon dioxide. So in that stream, we are going to have nitrogen and carbon dioxide. So 2 components in each one of these streams. Since we don't know anything about this stream, you could label as the molar flow rate and the mole fractions, or you could label it as the actual flow rates of each component. I'm going to do it the second method this time. In general, when there's no information given about the whole stream, sometimes it is easier to label as the actual moles because there are less unknowns to solve and you're not multiplying unknowns together. So we have our carbon dioxide and our methanol in stream 1, carbon dioxide and nitrogen in stream 3. Now we have fully labeled our diagram. Let's circle our unknowns and go ahead, and now we can do our degree of freedom analysis. The number of systems that we have our absorber, we have our stripper, and then we have our overall. So right now what I want you to do is to pause this video, try the degree of freedom for each one of these subsystems. Once you're done, restart the video and double check your answers. All right, welcome back. Hopefully you had a chance to try the degree of freedom. Let's go ahead and double check your answers. Let's start with our overall. Here, I'm just going to give you the answer for now. In terms of the overall, we have our 4 unknowns. We have NP in the product, our nitrogen stream, and then both unknowns in the stream 3 coming out of the stripper. In terms of the number of species that we have all 3 species. We have the carbon dioxide, not all the species, but we have carbon dioxide, we have methane, and we have nitrogen. What you actually see is that the methanol does not appear in any of those streams. It goes from the absorber to the stripper and then gets recycled back in. So it does not concern the overall at all. In terms of the absorber, we have 4 unknowns. We have 1 in the product, 1 in the recycle, 2 in stream 1. We have 3 species. We have carbon dioxide, methane, and methanol. And so nitrogen does not affect the absorber because it only goes in through the stripper. So we have a degree of freedom of 1. In terms of the stripper degree of freedom, we have our 6 unknowns, the 6 that circle around the stripper. We have our 3 species. In this case, the species that's not involved in the stripper is the methane. Methane is only around the absorber. And in this case, we were told that the nitrogen actually took out 90% of the carbon dioxide that was fed in the solvent, CO2-rich solvent. So writing that in terms of an equation, 90% of the CO2 that went in, which is 90% of CO2 in stream 1, is equals to the amount of CO2 in stream 3. So with that, you see that you have a degree of freedom of 2. Now some of you might be looking at one of the pieces of information that says essentially all of the methane that was fed into the absorber comes out as the product, and you might try to write that as a process specification. The reason why we are not using that as a process specification is because by the way we have labeled our diagram, we have actually already used that piece of information. How have we used it? We have used it because we did not label any methane in stream 1. So if you do a methane balance around the absorber, that will come out as all the methane from the feed goes into the product, simply because it was not labeled in stream 1. So that has already been used. We will not count that in our degree of freedom analysis. What you see here is an interesting case where we have no degree of freedom of 0, which means there's nowhere we can start, and it turns out that there's nowhere we can partially solve for anything that will cause something else to go to 0. What we actually observe, and it's actually stated in the question in the textbook, is to neglect the nitrogen stream that's going in and out of the stripper. Why is that so? Because if you do a nitrogen balance around the stripper, what you have is N2 is equals to N2 in stream 3. Both of these are unknowns. Unless you know one of them, you're not going to know the other, which means the nitrogen balance cannot be solved without knowing either of the streams right there. Because of that, we can actually just remove that. Both of them are unknowns. We don't care about the nitrogen, how much we're putting in, how much we're getting out. If we remove that, remove the nitrogen stream as an unknown, so now I have uncircled those unknowns, what you're going to see is that my overall now only has 2 unknowns, and we have our 2 species, which is our carbon dioxide and our methane. We have removed our nitrogen as well, but it actually causes our degree of freedom to drop to 0. Go ahead and verify the degree of freedom that I've shown here and how it has changed. The absorber has not changed because nitrogen does not affect the absorber. In terms of the stripper, you have reduced 2 unknowns. You have lost a balance, which is your nitrogen balance. And with that, your degree of freedom actually does drop, but it only drops to 1. So with this, you would solve the overall first. That will allow you to solve for your product stream as well as the carbon dioxide coming out in stream 3. And after that, your stripper degree of freedom should drop to 0. That will allow you to solve for that. And that should actually solve for everything that you need. You don't even need to solve for your products, the absorber after that. So I'm going to leave the solving up to you. You can see that there's actually not a whole lot of equations left to solve. There's mostly balances left in here with one specification. So I'm going to leave the calculations up to you. The solutions have been posted on the class website. So once you have finished solving, go ahead and verify your answers to make sure that you did the math correctly. So that's all we have for this video example. Work hard, be smart, and I'll see you next time.